So today we shall see the Polyginous formula, which is an application of the greatest integer function. So let n be a positive integer. Then you take the highest power of a prime p which divides n factorial. Suppose it is e. So let p be a prime number and suppose p raised to e exactly divides n factorial. That is, e is the exponent of the largest power of p that divides n factorial. E is the exponent of the highest power of p that divides n factorial. Then this e, this is the notation for exactly divides. That means p raised to e divides n factorial, but p raised to e plus 1 does not divide n factorial. Okay, that's the meaning. P raised to e divides n factorial, but p raised to e plus 1 does not divide n factorial. That's the meaning of p raised to e exactly divides n factorial. Okay. So that is the value of e. This e is given by the following formula. Then e equal to integral part of n by p plus integral part of n by p square plus and so on up to infinity. Or you can write this as summation integral part of n by p raised to I equal to 1 to infinity. This is the formula. Formula for the highest power of p that divides n factorial. Here you would observe that this is not actually infinite sum, because when p raised to I becomes larger than n, the integral part of n by p raised to I becomes 0. Okay? Note that. So this is the statement of the theorem. Note, for I such that p raised to I bigger than n, integral part of n by p raised to I equal the above sum is a finite sum. It's a finite sum. If for I bigger than s, p raised to I is bigger than n, we have E equal to summation n by p raised to I integral part I equal to 1 to s. You can stop at any value s such that p raised to I is bigger than n. You can take s to be the largest value of I such that p raised to s is less than or equal to n, and you can stop there. Alright. Now, to prove this, you can proceed by induction. To by induction on n. So what happens for n equal to 1? Highest power of a prime p that divides 1 factorial. So that is 0. So divides 1 factorial is, this is the power p raised to 0, and 0 equal to integral part of 1 by p plus etc. That's 0. So the result is true for n equal to 1. Now for convenience, let nu p n, capital N, for any integer n equal to the exponent of the highest power of p that divides n. Just take any integer n, du p n means the exponent of the highest power of p that divides n. Thus, p raised to nu p n exactly divides n, right? This is the highest power. P raised to that thing exactly divides n. That's the meaning. So we are interested in finding this p n factorial, and we want to prove the formula for this. So we assume that holds for n minus 1. That is nu p n minus 1 factorial is equal to what we are assuming, n minus 1 by p plus n minus 1 by p square plus and so on. This is true. We are assuming that this is true. We want to prove that nu p n factorial is equal to integral part of n by p plus integral part of n by p square plus and so on. This is what you want to prove. Now what is the difference between these? Difference arises provided n is divisible by p, then there is difference. So suppose n is divisible by a specific power of p. Suppose p raised to j exactly divides n. Then nu p n factorial equal to nu p n minus 1 factorial plus this j, right? Therefore, we have to prove that. Is it clear? N factorial is n minus 1 factorial times n, and this is the highest power of p that divides n minus 1 factorial. The power of p that divides n is p raised to j, so that j comes here. So this is true. So what we have to prove? We have to prove that, see, that difference between these two is j. Now here difference between these two is j, so we have to prove that difference between these two is also j. Difference between these two formulae should also be j. Prove that summation n choose p raised to I integral part minus n minus 1 choose p raised to I integral part. Take the difference of these two series. These are non-negative quantities. I equal to 1 to infinity. That should be equal to j. That difference should be equal to j. If we prove that, then from the result for n minus 1 you get this result, because this difference is already j, so this difference should also be j. So this will be proved. So how to show that this difference is j? So these quantities, see that there is not much difference between these two, that is to be observed. N is just next to n minus 1. So in the integral part of this and this, n by p raised to I and minus 1 by p raised to I, there is not much difference, but there can be sometimes difference. So when is there a difference and when is there is no difference? So suppose n is divisible by p raised to I, then this will be an integer and its integral part is itself, whereas this will be slightly less than that, and so its integral part will become just 1 minus this number. So difference will be 1 in that case. Okay. Whereas if p raised to I does not divide n, then we will be able to show that these two are equal. Difference is 0. So the difference is either 0 or 1. And when is it 1? It is 1 provided p raised to I divides n. That's what we will check. So how many times you get this difference as 1? If p divides n, it will be 1. That p square divides n. In that case you will get again 1. Up to highest power of p that divides n is p raised to j. So up to that you will get contribution as 1. And after that the contribution will become 0. Okay. So this will be equal to z. That is what we observe. So suppose p raised to I divides n, then n equal to p raised to I into some quotient q plus r. This r is 0. Later on we will consider when r is positive. So integral part of n by p raised to I is equal to q. Now what is n minus? N minus 1 is equal to p raised to I into q minus 1, which you can write as p raised to I into q minus 1 so minus so q minus 1 will be the quotient plus p raised to I minus 1. This minus 1 I have written over here, and this is adjustment p raised to I. And this is a quantity 0 less than equal to p raised to I minus 1 less than p raised to I. Okay, this is anyway positive. This is less than p raised to I. And therefore, if you take integral part p raised to I, that becomes q minus 1. Quotient is q minus 1. When you divide this by this, whatever quotient is there, that is the integral part. And therefore, this tells us that integral part of n by p raised to I minus integral part of n minus 1 by p raised to I, the difference is 1 in this case. Difference is 1. Now suppose p raised to I does not divide, p raised to I does not divide n. Therefore, n equal to p raised to I times q plus r. Q is an integer and r is an integer, 0 less than equal to r less than p raised to I. And here I can say 0 less than r because p raised to I does not divide n. So you can say r is bigger than 0. Now you write down n minus 1 is equal to p raised to I times q plus r minus 1. And now this is 0 less than r, I can write about r minus 1. So r is bigger equal 1 here, therefore this is bigger equal 0, and certainly it is less than p raised to I. Therefore, integral part of n by p raised to I minus integral part of n minus 1 by p raised to I, both are q and q. So q minus q. Both are q, quotient. Okay, because this is remainder, this is between 0 and p raised to I. So that is 0. And this gives you the required result. Thus, integral part of n by p raised to I minus integral part of n minus 1 by p raised to I equal to 1 if p raised to I divides n, 0 if p raised to I does not divide n. Thus, since p square of 2 raised to j divide n, but p raised to j plus 1, p raised to j plus 2, etc. do not divide n. This first j values divide n because p raised to j exactly divides n, that's what we are assuming. After that they don't divide. So how many values of I are there such that p raised to I divides n? There are exactly j values. Okay? There are exactly j values of I such that p raised to I divides n, just divides. Therefore, summation integral part of n by p raised to I minus integral part of n minus 1 by p raised to I equal to 1 to infinity. That comes out to be equal to 3. And j, we can say it is nu p of n. That is the highest power of p that divides n. Okay? And therefore, nu p, so this summation n by p raised to I equal to 1 to infinity minus summation n minus 1 by p raised to I equal to 1 to infinity, because both these are finite, so you can take the difference and that is equal to nu p n. But by induction assumption, this thing is what? This is nu p n minus 1 factorial by induction assumption. By induction assumption, summation n minus 1 by p raised to I, etc. is equal to nu p n minus 1 factorial. And therefore, summation n by p raised to I equal to 1 to infinity is equal to nu p n minus 1 factorial plus nu p of n. And when you add this, you get nu p n factorial. That's equal to nu p n factorial. That's what you want. So this proves the formula of the Polignacs. So example, find the highest power 3 that divides 1000 factorial. Highest power of 3 that divides 1000 factorial. So this is given by three dividing 1000 factorial is E equal to integral part of plus integral part of 1000 by 3 square plus integral part of 1000 by 3 cube plus integral part of 1000 by 3 raised to 4 plus integral part of 1000 by 3 raised to 5 plus integral part of 1000 by 3 raised to 6. So this is 81. Here 729. There we have to stop. After that 3 raised to 7 will become bigger than 1000. So that integral part will become 0. So we get to stop there. And now find out this thing. Divide this by 3. So 333 plus divide this by 9. So that is 111. Divide this by 27. So that comes out to be 37. Divide this by 81. That comes out to be 12. Divide this by 243. That comes out to be 4. Divided by 729. That comes out to be 1. But here, notice that we have divided by 3, 9, 27, 81, 243, 729. But it is not necessary to divide by these different numbers because of the property of the integral part function. How do you obtain this? You can use this and get this. So illustration is 1000 by 9 is equal to integral part of 1000 by 3 by 3, which is equal to integral part of 1000 by 3 by 3, and this is, what is this? Already obtained, 333 divided by 3, that is 111. See that the answer that we have obtained is smaller than this number, and you are dividing also by only 3. So that is a simpler calculation. And now if you understand this, then same argument you can use here. Instead of this we have obtained. Now this can be considered as 1000 by 3 square integral part divided by 3 integral part. So divide this by 3 and take integral part. Divide this by 3, take integral part. Answer is going to be same. Okay. So that is a simplification for this calculation. So you will now see, so etc. You can do this simplification. So let me use this and do the following calculation. So find the highest power of 7 that divides 1256 factorial. So answer this is 1256 upon 7 raised to I, summation I equal to 1 to infinity. This is the formula. E equal to. This is the answer. What is this? Divide first of all this by 7. That's equal to. So 179. Now this is the first one. Next term is, don't divide by 7 square this number. Divide this by 7. That is the next term. So what is the next term? 23. 25. Okay. 179 plus 25 is the next term. You divide this by 7. So this. Now again 7 cube, you have to divide this by 7 cube and take integral part. To do that, just divide this by 7. So what do you get? 3. Now divide this by 7. That's 0. So we have to stop there. So this comes out to be 207. So that is the answer. So you see that you don't have to worry about which power of 7 becomes bigger than this. We don't have to see that because you have got the first number, go on dividing that by 7. Somewhere you stop. So a modification of this problem is the following. Find the zeros at the end of 1000 factorial. Zeros at the end of 1000 factorial. So how do you get 1 0? 0 is obtained by 10 factor, 10 dividing this number. 10 is 2 into 5, contributes to 0. Suppose there are 5 zeros at the end, exactly 5 zeros at the end of a given number. That means 10 raised to 5 will exactly divide that number. Now 10 raised to 5 divides means 2 raised to 5 should divide and 5 raised to 5 should divide. But 6 powers of them may or may not divide. See that. Suppose 2 raised to 7 divides a given number, but 5 raised to only 5 divides the given number. Then suppose 5 raised to 5 exactly divides n and 2 raised to 7 divides n. This is larger power than this. Then you will see that 10 raised to 5 will exactly divide n. This is the minimum of these two. Okay. So we have to find out what is the highest power of 2 that divides n factorial. Find the highest power of 5 that divides n factorial, like 1000 factorial. And take the minimum of these two powers. Now, can you tell me which one of these powers, power of 2, power of 5, is larger and which one is smaller? We expect that 2 is smaller prime, therefore highest power of 2 that divides n factorial will be bigger equal highest power of 5 that divides. That is what you expect. Can you prove it? That, so this is just a note. If P1 or P and Q are primes, P less than Q, then highest power of P, now I have given this notation nu P, n factorial, P the smaller prime is bigger equal nu Q n factorial. This is what you expect because P is smaller prime, so it may appear more times in n factorial. How do you prove this? Using the formula of the Polignac. What is nu P n factorial? Summation n by P raised to I equal to 1 to infinity. This is integral part of n by P raised to I. But now you see that P is smaller than Q. So this is bigger equal summation integral part n by Q raised to I. Because this is larger than this, denominator is larger. So the number is smaller means integral part is also smaller. So this is bigger equal this, summation is bigger equal summation. And this is okay. What you expect is true, that can be easily proved by using the formula of the Polignac. Another note that we should understand is that the Polignac formula is true for primes but not for composite numbers. You cannot directly use here highest power of 10 that you want. So 1000 upon 100 plus integral part plus 1000 upon, so 10, 100, you cannot do that because 10 is a composite number, and for which, so the Polignac formula is not true for composite numbers. If P is composite and then you want to find highest power of this composite number P that divides n factorial, then that n by P integral part plus n by P square integral part, that formula is not true. So you have to look at the factors of that composite number, and from that you can get the conclusion. Since number of zeros at the end of 100,000 factorial is equal to highest power is equal to the exponent of the highest power of 10 that divides thousand factorial, say nu 10,000 factorial. We find (10,000) factorial and nu 10,000 factorial, and take the minimum. So I will just remove this and then do it again. So but nu 2 1000 factorial is bigger equal nu 5000 factorial. And therefore, number of zeros at the end of 1000 factorial is equal to nu 5000 factorial. You don't have to calculate nu 2000 factorial. And this is, as you know, 1000 upon 5 plus 1000 upon 5 square integral power plus and so on, which is 200 plus divide this by 5 and take integral power, so 40, divide this by 5 and take integral power 8 and finally 1, and that becomes 249. If you want to find out, say, highest power of 45 that divides 1490 factorial, suppose you want this, then you observe that this is 3 square into 5. So you have to find out nu 3 1490 factorial. Nu 9 will be half of this. Half of this, integral part of that, okay, and then take nu 5 of 1490 factorial. These two quantities are there. Take the minimum of this, and that gives this answer. Okay, you have to do it this way because 3 is appearing 2 times and 5 is appearing once. Suppose you want a binomial coefficient, let us say 1000 choose 476 binomial coefficient. And what is the highest power of a prime p? Nu p of this number for a prime p. You want to find this. How you find that? This is 1000 factorial upon 476 factorial multiplied by, so this is nu p 1000 factorial upon 476 factorial into 524 factorial. So this is highest power of the prime that divides this minus highest power of p that divides this minus highest power of p that divides this. So it is nu p 1000 factorial minus nu p 476 factorial minus nu p 524 factorial. That is the answer. You can calculate it this way. So you can try other problems of this type. Okay. Time is over ना संपला वेळ काय आहे अजून थोडा आहे 15 मिनिट आहे मी मगाशी मी काहीतरी खून केलं म्हणून म्हटलं ओके so there is some time so I will do something more. So we will do the days of the week, the day of the week from the date. So we will have some nomenclature like this. To get the day, we get, so define n so n is the number of the day in the month. M is the number of the month counting from March. For example, if we have the date, let us say 20th April, for this n will be equal to 20 and March is 1, April corresponds to m equal to 2. Now see hundreds in the year. And why? The last two digits in the year. Like if the year is, let us say 2055, then C is equal to 20, Y is 55. In addition, we have L equal to 1 for leap year and L equal to 0 for a non-leap year. Also, D equal to 0 for Sunday, 1 for Monday, etc. Then D, that is the number corresponding to the day, is given by the following formula. Then D, that is number corresponding to the day for a given date, is given by the formula is D equal to n plus integral part of 2.6 times m minus 0.2 plus y plus integral part of y by 4 plus integral part of c by 4. C is number of centuries, plus, so minus 2 times c minus 1 plus L times integral part of m by 11. So n plus integral part of 2.6 m minus 0.2 plus y plus integral part of y by 4 plus integral part of c by 4 minus 2c minus 1 plus L into integral part of m by 11. This whole thing, this number that you get is congruent to D mod 7. Mod 7. This is a complicated looking formula. If you do the calculations, you will get the number corresponding to the day. So if this calculation comes out to be, let us say 3, then 0 means Sunday, 1 means Monday, 2 is Tuesday and 3 is Wednesday. So you get Wednesday as the day of the corresponding date. And the integral part function is used in this. Here there is L for leap year. So leap year is an year which ends with 2 digits, which are, that number is divisible by 4. Okay. So 1952, that is a leap year. 1953 is not a leap year. However, for centuries one has to be careful. Is 1900 a leap year? So this is divisible by 4. Last 2 digits you have to look at. Divisibility for a given number by 4. We should look at last 2 digits. So although this is divisible by 4 and this is also divisible by 4, only this is leap year and this is not. The rule for centuries is different. The century year, that should be divisible by 400. Then only we say that it is a leap year. So this is not a leap year and this is a leap year. There is a different rule for leap year. Okay. Now, what is the proof of this result? And can you calculate the value of D using this formula. So, what is 2nd of October 2010? So here N number of the month, but number of the month you should start from March. March M equal to 1. So March, April, May, June, July, August, September, October. October is 8. So N number of the month is 8. What is the value of N? Number of the day in the month. N is equal to 2. What is C? Hundreds in the year. Centuries, that is 20. What is Y? Year. 10. What is L? Leap year or not? This is not divisible by 4. So L is 0, not a leap year. So try to calculate this number now. So N is 2 plus 2.6 times M, 8 minus 0.2. So it is this comes out to be 20. Okay. Then plus Y plus 10 plus Y by 4, that is 2, plus centuries by 4, that is 5, minus 2 times centuries, that is 2 times 20, that is 40, minus 1 plus L, L is 0, so that is 1 only, so minus M by 11, 8 by 11 integral part, that is 0. And then you have to see what it is mod 7. So you can do the correction mod 7, so 2, this is 20 means minus 1 you can say, this is 3, this is 7 means 0, now this is minus 5, that is 2, and so this comes out to be 1, 5, 6. What is 6? See, 0 is Sunday, so 6 is Saturday. This means that on 2nd October 2010 there was a Saturday. Alright, and the proof is by induction. You assume that the result is true for a specific day. Okay, first of all, on this day, for example, you verify that the result is true. We already know that it was a Saturday. Now, what happens on the next day? If the result is true for a specific day, what happens for the next day? And what happens for the previous day? So, from that, you can give the proof of the formula for the day of the week. So, proof is by induction. Assume that just verify for a specific day and check for the next day. What are the changes in the next day?